All right, so beyond the like dissolves like, temperature and pressure can help dissolve things sometimes as well. We'll get into that here. So, what you see on this graph is it shows you how many grams of a solute can dissolve in 100 grams of water as a function of temperature, right? And the big trend that we see here is that as the temperature goes up, more stuff can dissolve. So, if I look at the sodium acetate right here, so I can dissolve almost 40 grams of this stuff when the water's really cold, borderline freezing. But as I warm that water up, let's get it up to like 60 degrees. 60 degrees, I'm over, gosh, that's like 110 grams. All right, so way more stuff dissolves in hot water than does in cold water. All right, and so that is the general trend. Don't worry about this little weirdo over here. We're gonna stick with the nice normal ones. All right, so when you're dealing with temperature, most solids and liquids will dissolve more readily in hot solvent. So heat things up to dissolve more stuff. It's another good reason, like, have hot water when you're washing the dishes because it helps dissolve more crud. All right, let me click this. All right, gases are a little bit different though. Actually, they're a lot different. They actually get more soluble the colder it gets, because the colder it gets, the slower those particles move. And the slower they move, the more those intermolecular attractions could help it dissolve. So it's really, you want them kind of going slow, but also the heavier they are, the stronger the London forces they're going to have will be. Most things that are gases tend to have pretty weak forces. That's why they're gases. So what you need to remember is large molecules are going to dissolve better into a solution, and also low temperature is going to help dissolve you into solution. Let's talk about pressure really quick now. So pressure. Right, the solubility of liquids and solids doesn't change a whole lot with pressure, right? So if I take a rock from my backyard and I put it in some water and then I like squeeze down on the container, like that pressure is not going to help that rock dissolve. If I take oil and water and I try to crush them down with a piston, it's not going to help them dissolve. But gases, like I said, they're different. So the solubility of a gas in a liquid is going to be directly proportional to the pressure. So if I increase the pressure, all right, if I'm push down on this thing, right, increase that pressure, that's going to force more of these gas particles into the solution. Right, so the solubility is directly proportional to pressure. Hey, we could write an equation. Dun, dun, dun. Right, it's called Henry's law. So it just says the solubility of a gas is directly proportional to the pressure. This K, this is a proportionality constant. K stands for constant because chemists can't spell. All right, this K is really particular. It's for a particular gas at a particular temperature in that particular solvent. All right, so that's pretty specific. All right, so oxygen dissolving in water at 25 degrees Celsius would have a certain value of K. And that's going to be different than oxygen in water at 30 degrees Celsius or carbon dioxide in water at blah, blah, blah. All right, so there's probably huge lists of K somewhere, but we can kind of get away with not knowing K. We can do a lot of these calculations without actually getting the value of K. If we're staying at the same temperature, all right, then K is a constant, and I can push everything over to one side. So solubility divided by pressure equals constant. Therefore, initial solubility divided by initial pressure equals final solubility divided by final pressure. So if I change the pressure, this shows me how the solubility changes. Really easy. And for this thing, losing my voice here, units on solubility, I've seen all sorts of stuff. I've seen molarity, I've seen grams per liter. It could be, those are the two I've probably seen the most. Pressure can be anything. Atmospheres, as long as they're the same on both sides, it's good. So that's Henry's law. All right, one last little thing here. Here's a nice short video. Just kind of summing things up. And even some of the stuff I haven't even mentioned yet. So I'm going to mention it here. All right, when you're making solutions, if you're adding like a solid or a liquid into another liquid, right? So solids dissolving into a liquid or liquids dissolving into a liquid, that rate that the thing dissolves is going to increase with temperature. So how fast it dissolves. If you increase the temperature, these will dissolve faster. All right, if you put a sugar cube into iced tea in the summer and stir it around, it might take a while to get it to fully dissolve. But if you drop a sugar cube into hot tea, right, it's going to dissolve a lot quicker. So the high temperature will actually speed it up. Plus, the high temperature will allow you to dissolve more solute, which you actually saw at the very beginning of this. The other things of which I haven't mentioned yet, agitation. When you stir something around, right, you're bringing fresh solvent in there to help solvate that your solute. So that keeps swirling in the new stuff to come pull off those particles and bring it into the solution. Also the surface area, how much contact you have between your solute and the solvent, right? If I have a 1 gram sugar crystal, like pure sugar, just a 1 gram crystal of it, and then I have 1 gram of sugar, but powdered sugar, and I go to dissolve both of those, the powdered sugar is going to go so much faster. You're going to put it in and poof, it's pretty much going to like disappear instantly. Lots of surface area, lots of places for it to interact with the solvent. Going over to gases. All right, what I always tell people when we're talking about gases, the ideal conditions to dissolve a gas would be low temperature, high pressure, no agitation, right? Think of that. That's normally how you store your soda, right? If you got a can of Coke, right? Out in the fridge, it's cold. It's just sitting there and it's under pressure because that can's closed. Right? When you do open it up, when you do pop the top and take the pressure off, right? If it hasn't been agitated and it's really cold, it's just going to go and open. It'll be fine because that the CO2 that's dissolved in there is going to be relatively happy. It's like, okay, I'm fine here. But take that same can of Coke, put it in the back of your car, let it get nice and hot and toasty, leave it out there for a couple days, go off-roading, bounce it all around the place. All right, so it's at a high temperature, it's been agitated. It might still be under pressure because the top's on, but as soon as you pop that top, it's going to go and explode all over the place. All right, so that's because high temp and agitation are not things you want to have a gas be soluble in a liquid. All right, I will catch you in the next one. See you there.